So let's start with some examples. The first example I want to go through is essentially a simple one, and one that you've probably seen before in terms of the setup. So we're going to start with something familiar and then move on to things that we haven't seen before. So example number 1 is asking us, find the magnetic field at an arbitrary point P on an axis or on the axis of a circular loop of radius A carrying a current I. So the first thing I want to do is draw a diagram. And that diagram involves drawing my circular loop, which is essentially a current carrying wire that's bent into a circle. So let's draw this as this. There's my current carrying wire. We're just going to assume that the current's going this way. I am going to need an axis, and usually that axis is going to just come straight out. The center of that loop. So I'm going to call this the x direction. And what else are we given? We are given that the radius of this loop is A. Let's call this A. We also know that there's a point P. So we'll put a point P here. That's an arbitrary point. So we have our I, we have our A, and we have our P. So let's write down a few things. And these are things you won't have to write down if you are approaching this question, but I'm just going through this step by step. So the Biot-Savart law determines your differential magnetic field element at a point P. So we must identify the vectors dl and r. So the requirement for the Biot-Savart law is dB is equal to your permeability of free space over 4 pi, and then you have that term where you have I times dl crossed with r. So the most important thing is to figure out where these two vectors are. So these two vectors, I can kind of see that. I'll just take the top part here as an example of the wire. The tangent to this small segment is essentially my dl. Now r is going to be the direct distance from that particular point in the wire to my arbitrary point. So that means my r has to be in this direction. So then I take a look at what I have, and I want to at least mention that dl and r are going to be perpendicular to each other. And that's fairly obvious because my r is pointing away from any of the tangents of the ring going around the ring. So then the next thing I want to do is label some sort of angle here between r and a. So this would be theta. And just keep in mind that this distance from here to here is r. So I can actually come up with an expression for cosine of theta, which is adjacent over hypotenuse, A over R. Okay, so that's the most I've labeled so far. When we go around a ring, we want to figure out what happens to dB. So, also something you don't have to draw, but if I take a look here, I have my ring, and I have my axis. I also have my point P. If I look at my DL crossed with R, and I know that it's going to be DL first and then R, I use my Fleming's left-hand rule or right-hand rule, and I find out that I have a dB that points away from all of this. So I'll say my dB is going to point this way. And in order for dB to be perpendicular to both DL and R, we have this as our angle theta. And this would be at right angles. So now that we have this, I can kind of presume that at all of these points, along my circular wire, they're going to contribute differently. So the top one is going to contribute to point P and have a differential magnetic field element that points up like this. So this is from the top. From the bottom, I have a contribution that looks like this. So what this tells me is that my vertical components and my horizontal components are going to cancel each other out. So the only component that remains is simply the x component. So I essentially would have a whole bunch of arrows going like this, and the resultant vector is simply going to be dpx in the x direction. So when we go around the ring, the dB components that are perpendicular to the axis will cancel, giving a net magnetic field along the x-axis. So we've analyzed its symmetry, and we know we now have to figure out dpx. So that means we just need to find dbx and integrate. So why don't we go ahead and do that? I usually like breaking down my problems into the Biot-Savart law, like find your dB first and then just integrate. So step number 2 is essentially just the Biot-Savart law. And why don't we just start by saying we know that dB is equal to mu naught over 4 pi. I dl crossed with r over r squared. So how can I rewrite some of these terms so that I can do a proper integration? number one, what is dbx? So if this is db, then technically dbx is equal to db cos theta. So let's write this down, db cos theta. What else do we know? We know that cosine of theta was a over r. And apart from that, we know that r is equal to, looking at this triangle with a right angle, we have a squared plus, oh, there's one thing we haven't mentioned before, is the distance that p is away from the origin. So x squared plus a squared equals r squared. So r is equal to the square root of a squared plus x squared. So those are three relationships that we can obtain from our diagram. There are some other things we have to look at. So I can replace my r. I can replace my, let's see. I know I have to solve for dbx at some point. I do have to be able to replace my dl crossed with r, so that's the next thing I want to do. Let's take a look at dl crossed with r. And we know dl is perpendicular to r, so theta is equal, or I guess we'll do phi just in case, is equal to 90 degrees. So we have dl r sine 90, which is just 1. We also know that the magnitude of a unit vector is simply 1. So dl crossed with r is just going to be dl r sine of 90, which is simply dl. So now we can go ahead and replace a whole bunch of these. I know that db is equal to this, and I know db can be reduced to mu naught I dl over 4 pi r squared. But what I really want to find is dbx, so I move into just solving for dbx, and that's equal to mu naught I dl over 4 pi r squared times cosine of theta. And I know that the cosine of theta is a over r, so I'm going to say it's this, a over 4 pi r cubed. But I also know that r is the square root of a squared plus x squared, so that means I can rewrite this to get mu naught I dl a over 4 pi a squared plus x squared to the power of 3 over 2. So now I'll be able to integrate. So I know that b is equal to the integral of dbx, and it's going to be in the x direction by inspection. So then this is equal to, we'll first figure out all the constants. So I know mu naught, 4 pi, I, and a, all of those are constants. So I can factor all of those out, mu naught IA over 4 pi. And I'm going to integrate dl over x squared plus a squared to the power of 3 over 2. So is there something else I'm missing over here? Looking at the diagram, a squared plus x squared has nothing to do with dl. So we really should have factored that out at the beginning. So this is also something to factor out, which means I have mu naught IA over 4 pi x squared plus a squared to the power of 3 over 2 times the integral of dl. And what exactly is dl? The integral of dl is simply going to be the length of the ring, which is a circumference. And that circumference is 2 pi r, but the radius is a, so we have 2 pi a. And that means I have b being equal to mu naught IA 2 pi a divided by 4 pi x squared plus a squared to the power of 3 over 2 in the x direction. So if I want to simplify this, I have b is equal to mu naught I a squared over 2 times x squared plus a squared to the power of 3 over 2 in the x direction. And that is your answer for the total magnetic field at an arbitrary point P away from the axis of a circular loop that carries a current.